Hello, Honors Bio people. I'm going to rerun through a little bit of this today because I know a few people that were remote had a difficulty or a difficult time accessing some of the content because of the slow internet. So I figured I'm just going to do a video and I'm going to cover the rest of the PowerPoint here, and we'll do some other things in class. I'm also going to do a couple screencasts of my iPad and some of the drawings that went over today. So here's the periodic table, sometimes called the periodic table of elements or a periodic chart. Notice there are a bunch of elements missing. There's somewhere in the neighborhood of 94 elements that exist in nature, and about 20 or so that are man-made. But they all do show up on the chart. I've simplified this one a little bit, and I've only put in the elements that are relevant to biology. So it's about the first 20. A couple things that you need to know: the families go up and down, or in columns, if you will. And periods go across side to side in rows. So up and down are families, which are columns. Now, this is a mistake here. It says side to side and top and bottom. Make sure you cross that out. I'm just noticing that. But columns go up and down in our families. Things in the same column look alike, act alike, have the same number of electrons in their outer shell. Periods go 1, 2, 3, 4, 5, 6, go down, okay? And these periods, as you're going down, 1, 2, 3, 4, 5, 6, this is a period. H and He is period 1. Li, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon are period 2 or row 2. So rows and periods are the same, families and columns are the same. Once again, here's just a list of the symbols and the elements that go along with that. Fluorine is actually incorrect, should be F. So, quick intro to chemistry. So what's matter? So matter is anything that takes up space and has mass. So virtually everything on the planet takes up space and has mass, even things like air. If you were to take a balloon and blow a balloon up with the carbon dioxide and nitrogen that comes out of your lungs, you tie a knot and say this balloon, you could actually take that balloon and weigh it on a scale that, or balance that was pretty precise, and you could actually measure or weigh the amount of air inside, which is pretty neat. So living things and non-living things are made of the same kind of matter. That is a true statement. So, for example, I have carbon, oxygen, hydrogen, nitrogen, and me, which makes about 90%, 96% of my body. That matter is the same. That's the same stuff that's found in like rocks and inanimate objects. So living and living things have the same kind of matter. The other thing with matter, you can't create it or destroy it. It can only be recycled or reused through an environment. So states of matter. Matter comes in, and these are things you might have seen in 7th or 8th grade. Matter comes in 3 forms on this planet: solid, liquid, gas. So if we look at from a space standpoint, a solid takes up the least amount of space. A liquid takes up a little bit more space. Gas can take up a lot more space. Another thing we could look at is how the molecules are in there. So if you take a gas, right, let's say like a water vapor, and it takes up and it has this large volume, if I start to squeeze the volume down of this gas, eventually gas turns into a liquid because the molecules get really close together, so it starts to become liquid or flow. If I continue to compress those things, I get a solid. All right, so as you start with a gas and you push and add energy and pressure to it, it turns into a liquid. When you compress it even more, it turns into a solid. Okay. Think about water is kind of one of the strange ones that normally liquids take up more space than a solid. In the case of water, that's one of the properties of water is that water takes up more space as a solid than a liquid, which is why it floats. It's a neat little thing. So what's an element? An element is a pure substance. So on the periodic table, once again, there are 94 naturally occurring elements with about 15 to 20 that after number 94 that are all man-made. These elements cannot be broken down into simpler kinds of matter. It is a true statement, but there are some differences to that. For example, some man-made elements, such as uranium is a naturally occurring, but something like uranium, it can be split through something called fission, and as it splits, it breaks into two smaller elements with the same with the same atomic components, so meaning electrons, protons, neutrons. Doesn't happen for the most part in nature. That's something that's a man-made cause. Parts of the atom. So once again, some review stuff. Nucleus obviously is in the center of the atom. Okay, the nucleus has this core made up of protons and neutrons. So protons are positively charged, neutrons are negatively charged. And I'm going to grab a couple magnets. I'll be right back. If you think about magnets, okay, so these are two magnets here. If I have them positive and negative facing each other, they clip together, just like that. Positive and negative, they'll clip together. Opposites attract. Neutrons have no charge, so they're neither positive nor negative. If I take the magnet and I flip it, and I have two positive charges or two light charges, I can't put it together. I can push and push and push and try, but it wants to keep repelling. Okay, so so imagine that you're inside the nucleus, and there are two positively charged things, and they're trying to push towards each other, and they can't because they repel each other. The neutron's job is to allow them to get close together, all right, without actually repelling each other. So that's what the neutrons do inside the nucleus. So in the nucleus, protons and neutrons, they each have a mass of 1. Every single, the electrons are on the cloud on the outside, which we'll talk about in a second, but when we talk about smaller of the two numbers, that also tells you the number of protons and electrons in that atom. Right? All atoms with the same, all elements that are the same atom will have the same atomic number. For example, all carbon atoms all have 6 protons. We can talk about the electron. The electrons are these things that are negatively charged. They're found around the outside of the nucleus, and they're moving. They're physically moving around. And as they move, some of them spin clockwise, some of them spin counterclockwise, and their movement is has a direct effect on the temperature of something. So, for example, the faster the electrons move, the higher temperature something is. Their other role is they play a major role in bonding, whether it's ionic or covalent bonds. So here's an example of like an oxygen atom. I would have drawn it a little differently, but this is, so we have 8 protons, 8 neutrons in the middle. We have 2 electrons in one ring. In this case, 6 electrons in the other ring. I would have put them at 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock, and then had one pair up top that are paired together. But this model is acceptable though. So chemical bonding. So we're talking about bonding. We're gonna draw some pictures about with this as well too. But this is just kind of to give you an idea of the two types. There's covalent and ionic. Covalent are the stronger of the two types of bonds. Covalent bonds, they share electrons. Okay. What I will give you another video and I'll draw a couple of these. So in the covalent bonds, electrons are shared between two adjoining or side-by-side atoms. Okay, for the most part, they're shared equally. There are some exceptions to that where they're not shared equally, which we'll get into a little bit. One example of this would be a bond between hydrogen and oxygen in the water molecule. Another type of bond is called an ionic bond. An ionic bond is a very weak bond. An example of an ionic bond would be sodium, Na, and Cl, chloride, or sodium chloride, which is found in table salt, or is table salt. If you take table salt and you put it in water, it dissolves. And the reason it dissolves is because it's a very weak bond between the two molecules, and it goes from being this hard crystal to invisible. All right? And the water actually is what causes it to dissolve. All right? But they work, once again, I'll use my magnets again. I'm going to keep away from my computer this time. I think that's what was the issue. All right? They work like magnets. All right? So if I think of a positive or negative magnet, right, they stick together. All right? The same idea with ionic bonds. You have a positive and negative element that are magnetically stuck together. All right? They're easy to separate. Right? When they're covalently bonded, not so easy to separate. So once again, my examples: sodium and chloride. They have there's two types of ions. There's an anion, which is negative, and a cation, which is positive. Not really something you need to know per se. Elements of life. Well, there's the big four are carbon, oxygen, hydrogen, nitrogen. You will need to know lots about those particular four. Excuse me. As for the other elements, phosphorus, calcium, potassium, and sulfur make up pretty much the rest. And then there's traces of other elements found in our body that we still need. For example, iodine is one of those trace elements, but iodine is used here in your thyroid gland, which is right behind your Adam's apple, which we all have. And the thyroid gland helps you regulate body temperature and helps you regulate metabolism. So if you have either too much or too little iodine in your body, it has an effect, either a slow or fast metabolism. All right, that's it on this. I'm going to stop here. I'm going to go back, do a quick edit, and get rid of my goof up out of there. And what I'll do is